Good morning. In today's lesson, we will discuss about resonance, beats, and the Doppler effect, still in the topics of sound wave. The word resonance comes from Latin and means to resound or to sound out together with a loud sound. Resonance is a common cause of sound production in musical instruments. One of our best model of resonance in a musical instrument is a resonance tube. It is a hollow cylindrical tube partially filled with water and forced into vibration by a tuning fork. Resonance can occur only when the first object is vibrating at the natural frequency of the second object. So if the frequency at which the tuning fork vibrates is not identical to one of the natural frequencies of the air column inside the resonance tube, resonance will not occur and the two objects will not sound out together with a loud sound. Here I have the Barton's pendulum. Barton's pendulum may be used to demonstrate resonance. The apparatus consists of a set of light pendulums made, for example, from paper cones, and a more massive pendulum or the driver, all supported on a string. The lighter pendulum have different lengths, but one has the same length as the driver. This has the same natural frequency as the driver, and therefore it will vibrate with the largest amplitude of all the pendulum. In the experiment of a resonance tube, the first resonance occurs when the length of air column inside the tube is 1/4 lambda. The second one will occur when the length of air column is 3/4 lambda. The third one will occur when the length of air column is 5/4 lambda. And we can make an analog with a vibrating string. So the length of air column when resonances happen can be given by the equation of Ln equals to n minus 1 multiplied by 1/4 lambda, where n is 1, 2, 3, and so on. When there is the first resonance, then n will be equal to 1. So the length of air column will be 2 times 1 minus 1 multiplied by 1/4 lambda equals 1/4 lambda. The second resonance when n equals 2 and so on. Let us see your physics book on page 173 and I will discuss the example problem number 1. In an experiment using resonance tube, the first resonance can be heard when the water surface inside the tube is 20 cm from the end of the tube. So L1 equals 20 cm. What is the length of air column to produce the second resonance? L1 is 1/4 lambda. It is equal to 20 cm. So when we want to find the second resonance, we want to find L2. That means that we have to find the lambda first. The lambda is equal to 80 cm, 20 multiplied by 4. So L2 is equal to 3/4 lambda or equals 3/4 multiplied by 80 centimeters, the lambda. So L2 is equal to 60 centimeter. Example problem number 2. The first harmonic of an open air tube of length 40 centimeter can be in resonance with the sound produced by a closed air tube. In resonance means the frequency are the same. For an open end air column, the first harmonic is F0. So F0 for the first column is V/2L1. So if I draw the diagram, there will be one node. And one node for the closed end will be like this. And this will be equal to the first harmonic, the fundamental note for the closed end air column. It is equal to V/4L2. Because here the number of nodes produced by both tubes are the same, so we have one node here and also one node there. So we have fundamental or first harmonic here, the open end air column, and also the first harmonic for the closed end air column. So if they are in resonance, that means that the frequencies are the same. So we have V over 2L1 equals V over 4L2. V, of course, will be the same because this is the speed of sound in air. So we can find 2 times L1, which is 40 centimeters, equals 4 times L2. Then L2 is equal to 20 centimeters. Our next discussion will be about beats. Here we have two sound waves, one of frequency 440 Hz and the other one of frequency 442 Hz. This is the 440 Hz and this is the 442 Hz. You may not be able to hear the difference between the 440 tone and the 442 Hz one. But when we play both, we can hear the phenomenon of beats. The phenomenon happens when two sound waves with slightly different frequencies interfere. Constructive interference, when the peak meets the peak or the part where the waves are in phase, will result in the loudest sound. Remember, amplitude determines loudness of sound. So if there is constructive interference, when the peak meets the peak, then the amplitude will be the largest, then there will be the loudest sound. And then the loudness will decrease until the peak meets the trough, or where the part of the waves are out of phase. There will be no sound because the waves cancel each other out. So there will be loud sound here, and then it's getting softer, and then no sound, and then it gets louder as the amplitude increases. So this is the part where the sound wave is the loudest, and then repeatedly it will go loud and soft, loud and soft, loud and soft, and so on. That's what we call beats. In this diagram, there are two sound waves with the frequency of 24 Hz and 30 Hz. The third wave here is the sum or the interference between the two. So there is loud sound and soft sound, no sound, and then loud and then soft repeatedly, with the beat frequency of f beats equals f1 minus f2, always in positive value. So in this case it is 24 minus 30. In positive value it is 6 Hz, or the frequency of the beats is 6 beats per second. I will discuss the example problem from your physics book, page 178. More problems, number 6. An open-end tube produces a fundamental note of frequency 249 CPS. CPS means cycle per second. It is equal to Hertz. A string of length 54 centimeters with a certain tension can produce a fundamental note of frequency 440 CPS or 440 Hertz. The tube is then blown stronger so that the first overtone is produced. So the first overtone will be twice the fundamental note. The string is shortened, becomes 48 centimeters at the same tension. Then it is vibrated together with the blown tube. The frequency of the tube was 2 times 249. It is equal to 498 Hertz. We want to calculate the frequency of the beats produced. So now the open-end column is blown with the frequency of 498 Hertz. And because f of the string is inversely proportional to the length, then we can find now that f is equal to 9 times 440 divided by 8. The f will be 495 Hertz. So the beats frequency produced will be 498 minus 495. It is equal to 3 Hertz. Another phenomenon that we can observe about sound wave is the Doppler effect. There may be times when you observe phenomena like this. When you are standing on the sidewalk and a car goes by you, this is the effect that causes the motor's frequency that you hear to be greater as it approaches you and smaller as it recedes away from you. This is called the Doppler effect. The Doppler effect is the change in frequency or wavelength of a wave for an observer moving relative to its source. In this diagram, we have a stationary source here, and if the source is stationary, we can see that the lambda or the wavelength is the same in all places. And when the source is moving towards the observer, we can see that the wavelength is getting smaller. When it is moving faster, the wavelength will be even smaller. So when a source moves towards an observer, then the observed wavelength decreases. So that's when the frequency increases. When a source moves away from the observer, you can see here the red diagram, the observed wavelength increases. That's when the frequency decreases. Remember, frequency determines the pitch. So when frequency increases, then the pitch is higher. When frequency decreases, the pitch is lower. So when a source is moving towards an observer relatively, then the observer will hear higher pitch. When the source is moving away from the observer, then the observer will hear lower pitch. We can write down the equation of the Doppler effect to be like this. Fo equals phi plus minus phi O over phi plus minus phi S multiplied by Fs. Fo is the frequency of the sound heard by the observer. O is the observer. Fs, this should be Fs. Please change in your book. This should be Fs. Fs is the frequency of sound produced by the source. Frequency of source, Fs. Phi O is the speed of the observer, and it will be positive when the observer moves towards the source, and this will be negative when O moves away from S. So this Phi O can be positive or negative. It will be positive when O moves towards S, and it will be negative when O moves away from S. Phi S, this should be Phi S, not Phi P. Please change it in your book. This should be Phi S, speed of the source, and it can also be positive or negative. It will be positive when S moves away from the observer, and it will be negative when the source moves towards the observer. You have to remember the signs there. And V is the speed of sound in air. What if there is wind, so that we should calculate the speed of the wind? Then when the wind blows in the same direction as the sound wave, of course the sound wave will get to the observer quicker. So Fo will be V plus V of the wind, the speed of the wind, plus minus V0 over V plus V of the wind plus minus Vs multiplied by Fs. We'll just have to add V with the speed of the wind, because we know that it will get to the observer faster or quicker. When the wind blows in opposite direction to the sound wave, of course that's when the sound wave will get to the observer slower, so that we need to subtract V with the speed of the wind. So the sound of wave sound wave, the speed of sound wave in air should be subtracted with the speed of the wind. So frequency of the observer equals v minus v wind plus minus v observer over v minus v wind plus minus vs multiplied by fs. I will discuss an example problem here. It is on page 175. Example problem number 1. Andy is standing near a sound source of frequency 676 Hertz. This is Andy, this is the sound source, 676 Hertz. Another sound source of frequency 676 Hertz is moving towards Andy with the velocity of 2 meters per second. The speed of sound is 340 meters per second. We want to find the beats frequency heard by Andy. Of course, the frequency of the sound here will not be heard by Andy at 676 Hertz because it is moving towards Andy. So the wavelength will be reduced so that Andy will hear higher pitch than the frequency of the source. So now we need to find the frequency that Andy hears, the frequency of the source that Andy hears. Yeah, V is 340 meters per second. We use this equation. F of the observer will be equal to V. This is the velocity of the observer. In this case, Andy is stationary, so the velocity is 0. And then V plus minus Vs, we can see that the source is moving towards the observer, so this should be negative. Of course, F of the observer should be higher than before. Then you'll need to subtract this with something. Yeah, and this should be multiplied by Fs. So we have 340 divided by 340 minus 2 multiplied by 676. It is equal to 680 Hertz. Andy is standing there. He is hearing sound source 1 with frequency of 676 Hertz. And he is also hearing the sound from the source that is moving towards him, so that he hears two frequencies. The one with 676 Hertz and the other one with 680 Hertz. So there will be frequency of beats that Andy hears, which is 680 minus 676, or you can do it otherwise. So it should always be positive. So the frequency of the beats is 4 Hertz. Now, you have to do the example problems in your book, page 173 and also 175. That's what we have discussed. You can do it yourself to check whether you understood or not. And then do the more problems in your book. Page 176, number 6, this has been discussed also. And then page 179, number 11 until 15. Of course, if you have any questions, you can always ask. I hope this video is useful. Thank you for your attention.